Hello, everyone. Welcome to this video where we're going to go over the topic of gas stoichiometry and basically talk about the procedure and how to approach these type of problems. So gas stoichiometry basically is like a follow-up to the main chapter of stoichiometry that we've seen before. Now we're just going to mix both topics about gas laws and the idea that we were working with on stoichiometry before. So you might remember this graph or this map that I used to call regarding stoichiometry calculations. So now we're going to add another variable to this particular map or graph, speaking about volume. Now, remember when we were talking about gas laws, we're talking about the ideal gas law mainly, which included pressure, volume, moles in the N, a constant R, and temperature in Kelvin, right? So we're going to use now these variables now as additional information when doing stoichiometry calculations. So in a way, it's important to consider the formula that we've been using for ideal gas law, as it's going to be part of this calculation approach, right? So remember, in this formula, we include volume, but we also have moles in this, right? So this is a perfect tool in order to transform or to convert from different units, specifically from liters to moles or moles to liters, liters being the unit of volume that we will be discussing. So a quick reminder of the ideal gas law: we include pressure either in atmospheric units, ATM, kilopascal, it could be, or millimeters of mercury. Volume, mainly in liters. Moles, as we have been discussing for more than a month now. The constant, which will be given, but it depends, strictly speaking, of the unit that we have in pressure. And the temperature, remember, if it's given in Celsius, we need to change it to Kelvin. If the answer requires us to give an answer in Celsius, then we subtract the standard temperature from the answer. So where before we had, the mass conversions between grams and molecules or atoms, both of them going to moles, and using this specific conversion factor, whenever we talk about volume, we're going to use the ideal gas law as the conversion factor, right? So this is going to be the tool that we need to use in order to go from either moles to volume or volume to moles. In other words, from liters to moles or from moles to liters. So remember, when going from grams to moles, we divide by the molar mass, and the other way around, we multiply. Regarding molecules or atoms or particles, all of this means the same. We multiply the moles times the Avogadro's number, or we divide by Avogadro's number in case we're going from molecules or atoms or particles to moles. Similarly, going from moles to liters, we will use the ideal gas law, but we will solve for V, for volume, right? So from having this original formula, we solve for V, or volume, which is the one that we don't have, assuming that we already have the moles, then we can fill in the spaces in there. If we're actually starting from liters and we need to get to moles, then the same formula we solve, but for moles now, right? So it's going to be the same formula, but depending on which one is our X or our unknown variable, we will solve the same formula for that particular variable. So it's important to consider that at this point, knowledge of gas laws and knowledge of stoichiometry is basic, right? So if you haven't mastered that yet, please go back and review that first. Otherwise, you can follow up with this video, right? So again, when we talk about volume, we'll be talking about liters. When we talk about mass, we'll talk about grams. We'll be using we will be using grams as a unit. So it's important that you remember this map. Pretty much is what's going on in all types of stoichiometry calculations. From grams, going from grams to moles, you divide by the molar mass. Going from molecules to moles, you divide by the Avogadro's number. Going from liters to moles, you use the ideal gas law, but solved for n, because at the end, n is moles, so that's what you want, right? Remember, when we are using stoichiometry calculations, we have two substances. So we need the mole-to-mole ratio, right, which is like a division or a fraction. And once we have the unknown substance moles, then we can go from moles to grams, multiplying by molar mass, or from moles to molecules, multiplying by Avogadro's number, or from moles to liters by using the ideal gas law, but now solving for V, right? So remember, if you're going from liters to moles, you have to use a formula. You don't divide by the molar mass. If you're using grams, you use a molar mass. Liters, ideal gas formula. Molecules, Avogadro's number. It's important to remember that a standard temperature and pressure is the 273.15 Kelvin. Pressure is 1 atmosphere. You can also have some values in kilopascal and millimeters of mercury as standard pressure. Normally, we would be using only atmospheres. And the ideal gas constant, that is dependent on the unit that we have in pressure. So if we have atmospheres, we're going to be using this number. If we have kilopascal in pressure, we're going to be using this number as a constant. And if we have millimeters of mercury, we're going to be using this number as well as a constant in these problems. So what now, right? So let's check out one example, right? In here, we're asked to calculate the number of grams, moles, and molecules, assuming we start with 600 liters of hydrosulfuric acid gas at STP. Remember, STP means the standard temperature and pressure. This meaning standard temperature, 273.15 Kelvin, and standard pressure would be 1 atmosphere or 1 atmospheric unit, right? So let's start. What are we given? The 600 liters, right? So it's important to remember that we're going to be using the ideal gas law for these type of problems when we have liters involved. So let's remember also that if we're considering STP, implying that this is 1 atmosphere, right? We're going to be using the constant that includes atmosphere in its unit, right? Temperature, remember, would be 273.15, right? All right, so let's continue. So we're going to be using this ideal gas law, but solving for n, right? Because consider again, by following the same map that we had grams, we had liters, and we have molecules, right? But remember that we cannot just go from liters to grams. Everything first needs to get to mole count, right? So in order to do that, we would be using this, right? In order to get moles. And then when we get moles, we can do something else, right? So as we have all of this information provided by the problem, so let's fill in the blanks, right? So for pressure, what do we have? Standard pressure, which is 1 atm, which is right here, right? The 600 liters is provided by the problem. So now we have the first section, right? Which is the numerator, right? P and V. What about the R? R is provided up for us over here, considering that is the unit of pressure, right? So we fill up this spot now, which is R, and then standard temperature, which is 273.15. So now we fill up this space and we have all of our information set up in our original formula. So we solve for this, we multiply and then divide everything, and you should get something around 26.79, right? With this, we have answered our first approach to the problem, which is get the moles, right? Now that we have moles, we can also go to grams and we can also go to molecules. So what are we going to be using? The moles, right? So we're going to be using this same moles or the answer that we actually got in order to find out the now the amount of grams that are present in this amount of moles, right? For that, we will be needing the molar mass of this guy, right? Of hydrosulfuric acid. So we do the calculations. So we do the math of this, and we will get a total of 34 grams per mole, right? Right over here. So we got this, and we just multiply, right, the moles by the molar mass, and we get the grams. Now for molecules, basically we need to remember for molecule side is the Avogadro's number. So when we're going from moles to molecules, we multiply by the Avogadro's number. At the end, we have already solved for all of these three aspects in our original problem. Second example, now look at this. We're starting with moles already, so this should make things easier, right? Again, we're mentioned about STP for chlorine gas, all right? So since we're starting for moles, let's go straight ahead into grams, right? So we need the molar mass of this chlorine gas molecule, right? Which is, you know, the molar mass of chlorine multiplied by 2, we get 70, right? If we round to the 35. So basically is the moles times the molar mass, and we get the amount of grams. For the molecules, we multiply by the Avogadro's number, and we're done, right? What about for liters? Liters is a little bit trickier, not really that much, but you require more than just a multiplication. We require a formula, right? So remember that we're going to be using the ideal gas law formula, but in this case, solving for V, for volume. So we're going to put our formula like this, you know, sending P, pressure, down as division to the opposite side, and we can replace the values within our formula. So for N, which is moles, is this moles that we're actually given in the problem. So this is going here. For the R, well, we're going to be using the one for STP, right? Because it's declared in here, which is 1 atmosphere. So we're going to be including it here. Temperature, standard temperature, again, 273.15. And then everything divided by the pressure, which has been declared before as standard pressure, which is going to be 1 atmosphere unit. So we do the math, and we will get 58.91 liters as the answer for this amount of moles of chlorine gas. All right, so now let's go ahead and do some sample problems. All right, so let's do the first example over here, and it says how many liters of carbon dioxide can be produced from 100 liters of methane if the reaction occurs under STP conditions. So what are we starting with? 100 liters of methane, right? What do we want? The liters, you know, XL of carbon dioxide, right? So in order to go from liters of carbon dioxide to liters of methane, we need to actually do the whole thing, right? So we're going to go from liters to moles, then to moles, and then to liters, right? So remember there's a barrier in here. So we're starting at methane and we need to go all the way to carbon dioxide. All right, so how is this approach? So in order to get from liters to moles of methane, we need the formula, right? So we're going to be using the ideal gas law formula, solve for moles. That would be N equals PB, pressure and volume, over RT, right? The constant in temperature, which is to say pressure is standard pressure, which is 1. Volume is the one that it's given in the problem, which is 100. The R, the constant, because it's STP, then we can use 0.0821, and the temperature as the standard 273.15, right? After you do the math, you will get around 4.46, right? Rounded to 2 decimals. But ideally, I do recommend that you keep the number from your calculator in there so you can continue working on this number. Don't erase it. You can just put there like 2 decimals so you can keep track of what you're doing. But I do recommend that you don't erase the number and continue forward with this. Let's put the last name of this, which is moles of methane, right? So now we have done this. Now we need to cross for the moles of carbon dioxide. And for this, we will do the ratio. So we'll have 4.46 mole of methane, right? We open the parentheses and we do the ratio. So first, let's put the unit. Remember, the one that you already have, put them in the denominator, the unit. So we're going to put the unit of mole of methane on the bottom, and on the top is the one that we want. In this case, it's carbon dioxide. So now that you have the units placed in your parentheses, you just need to check the numbers that you have in the equation regarding this particular. So methane is over here and carbon dioxide is over here, right? So if there is no number next to it, remember that's 1. So in this case, we will have 1 mole of methane equal to, or the ratio would be 1 mole of carbon dioxide, which logically, if we multiply and divide these numbers, eventually we will have the same number, right? 4.46 moles. But now we're on the other side, right? For carbon dioxide. This is moles of carbon dioxide, right? So now that we have the moles, we're missing one final step, getting to liters. So what do? We use the formula, ideal gas law, but now solve for volume. So this would require nRT over P, over pressure, right? Which is to say 4.46, which is your new moles, right? The new moles for carbon dioxide. The constant is going to be the same, 0.0821, and the temperature 273.15. Remember, these values are given for from the problem, including the constant. The pressure that we're actually using is 1 atmosphere, right? From the STP conditions. All right. So now you put these numbers in your calculator, 4.46 multiplied by 0.0821 multiplied by 273.15, and all of this divided by 1 will give you 100.01, right? So we can say 100, around 100 liters. This would be your final volume for, which one is it? Carbon dioxide, right? And this would be your final answer. Okay, so basically is step 1, going from liters to moles. Step 2, finding the ratio between moles. And step 3, going from moles to liters. This is to say that we will have step 1 in here, step 2 in here, and step 3 in here, right? In case you're asked for going from liters to grams, so instead of using this third final step, from these moles, you multiply by the molar mass. If you're going from liters to molecules, the last step, number 3, you multiply by the Avogadro's number, and so on and so forth, right? All right, so this is basically the overall explanation. I know it feels like oversimplified, but this is basically practicing. In the presentation, you have the rest of the problem, so you can practice with that. I have also shared with you in the same area where the presentation is the entirety of the examples of the problems, including the procedure and the answer for each. So what I do recommend is that you give it a try if you are still feeling unsure. Give it a try using the problems that you have in the presentation. And once you're finished with one problem, you can go to the document, check the procedure, check the answer. And if you have it correct, continue with the next one. All right, so hopefully that was useful just to connect the ideas of gas laws and stoichiometry. Remember, you can always send me an email, or if you have any questions, just let me know, and I can help you with anything that you need. All right, see you next time.